Okay, Algebra 1, Chapter 1.7. We're going to talk about functions today. What is a function? Does anybody know what a function is?
I know what it is, I can't describe it.
Can't describe it, okay? Yeah. Something does. Okay. Again, a function can be a rule, just like a relationship, right? Hey guys, I'm going to state this first. I don't know if it's on one of the other slides. How about, not that. A function I don't know what T implies, is a relation. A function is a relation, but a relation is not always a function. So let me back this up. A function is always, put a little thing there. A function is always a relation, because it's a rule. But just because there's a rule doesn't mean it's a function. Okay? That's big. But, okay, that still doesn't explain what a function is. So, okay, I've been saying it's a rule. It's a certain type of rule. This rule, guys, has to deal with your inputs and outputs. Here it is. Exactly one output for every input. There's exactly one output for every input. Now, I like to sometimes relate this to a soda machine. Is the soda machine functioning correctly or incorrectly? You go down to your favorite soda machine, Pepsi, Coke, whatever. So you go down there and you want to buy a Mountain Dew. Okay? So we're going to a Pepsi machine. You go down to that Pepsi machine, you hit Mountain Dew, you should get a Mountain Dew. You put more money in, you hit that same button, Mountain Dew. What should you get? A Mountain Dew. You go to that button again, and you push it, and you get a mellow yellow. Is something right?
Well, Mountain Dew's a Coke product.
Yeah, so therefore it's not functioning correctly, right? So, the whole idea is that every time I put the same thing in, I should get the same thing out. I keep hitting a Mountain Dew button, a Mountain Dew better come out. If I get something else, it's not functioning correctly. Now, I think we've all been to places in the mall or whatever, high volume areas, and the soda machine has more than one Mountain Dew button. Yeah, you've seen that before? So there might be 2 or 3 of them. All 3 of them, that's fine. 3 inputs that have the same thing, but they all lead to the same Mountain Dew. So therefore, that's still a function. You can have multiple inputs going to the same output. But if I hit that input, no matter which one it is, it has to lead me to the same exact output, and only one of them every time. So I've got 3 different ways on here, and we need to determine function, yes or no, and why. The first one is called a what? What kind is the first kind? What's that? It's a mapping. You should recognize I got mapping. I've got a second one, table or T-chart, and the third one is a set of points. The fourth thing we'll talk about is the graph. There's another way there as well. So this one goes pretty quick. So I look at the mapping, and I look at my inputs. They have lines going to outputs. Is this a function, yes or no? Look at the definition above. Is this a function, yes or no? I hear no. What else? There's only two options, yes or no. So I should hear some no's. I probably hear some yeses. Which one is it? Function? Well, first of all, is it a relation? Is it a relation? Yes, it's got inputs linked to outputs. It's a relationship. What you need to realize, guys, is that if I look at your inputs, do any of them repeat themselves?
No.
So the outputs repeat themselves. So if I put a 2 in, what am I going to get? Negative 3. Will that ever change? No. If I put a 0 in, I'll get a 6. Okay. I put a 3 in, I'll get a 6. Is it okay to have two inputs go to the same output? Right, it's okay as long as every time I put a 0 in, I get a 6. Every time I put a 3 in, I get a 6. And if I put a 4 in, I get a 9. This, ladies and gentlemen, is a function. There's only one output for every input. There's exactly one. That's your explanation. There's only one output for every input. Take a look at B. Function, yes or no?
No.
Why is it no, Fritz?
Because there's more than one.
Okay, that's not the only reason though. I agree. I think everybody should see that I got a 1 here and a 1 here. That doesn't take me out of the contention of being a function or not. Like, they don't have the same output. Notice the first one wants to go to a 4. But when I put it in again, it went to a 4. Or negative 4. What? Something's not functioning correctly. Something got off, right? Out of whack. That is not a function. Reason? Same input goes to two outputs. Is it a relationship? Is that a relationship, guys? Okay, let's go back to A. Is A a relationship? Yes, because functions are relations. Is B? It's not a function, but is it a relationship? Do they link inputs to outputs? Yes, it's still a relationship, guys. Any questions so far? You're looking for inputs to outputs. And part C, giving you a set of points. 2, 1, 3, negative 2, 3, 1, and 2, negative 2. Function or not function?
No.
No. Actually, I forgot to state that this one is not a function. And we would also say that this is not a function because, again, it's got 2's going to 1 and negative 2. That's no good. 3 goes to 2 different choices. It doesn't matter. One of them already basically breaks it. 2 of them just kind of verifies that it's definitely not working right. You guys get the idea of function and not function? Okay. So it's not too bad, right? Okay, turn the page. Okay, looks like a lot of words. There's a couple examples in here. Discrete function, guys. I already gave you the definition here. A discrete function is a graph that consists of points that are not connected. Can we think of a situation where a graph would not be connected? How about a graph that showed the innings of a baseball game and the number of home runs or hits? Is there anything going on between innings?
No.
Can you have half of a hit? I don't know. Baseball, do they count half hits?
Could that be a foul ball?
Well, I know, but it's still a hit, right? You hit the ball.
Yeah, but it doesn't really count.
So it doesn't count. So we just don't count it. So you would claim that you would put, okay, this inning had 5 hits, this one had 10 hits, right? You wouldn't necessarily mark a half of a hit, and there would be no connection of why you would need to put a line that zigzags from inning to inning, correct? I can see that. So what do you think a continuous function is? A graph with connected points. Yeah. That's a connected points. What kind of graph do we have for here then? Anybody got an idea? Someone give me a situation where if I graphed it, you would see a continuous line versus just individual. Things happen more than just when you're measuring. I mean, we got a situation below, but what do you got?
The more time goes by, the older you get.
Yeah, the older you get, right? Your age and time. So we counted in years, right? Generally, I'm so old and you guys are so old. But today, I'm not exactly the same age as I was yesterday, or even when I just started talking about this problem. I'm continuously, it's a nice, smooth curve, right? Actually, it would be a straight line, wouldn't it? Straight line. Time and age, because age and time don't speed up or slow down. You guys kind of see that? It's continuous. So, you would have points individually on here that we'd say, I was 1 year old at 1 year, and then I'd go to 2 years and 2 years, right? That type of thing. That's a continuous graph. A lot of times in math, we're going to deal with a lot more continuous graphs. But there are times we're going to talk about discrete graphs where it's just a set of points. So, I want you to draw some graphs here on this next one. The situation. There's a bird feeder that will hold 3 quarts of seed. I think it's supposed to be seed. Of seed. The feeder weighs 2.3 pounds when empty and 13.4 pounds when full. Can you make a table that shows the bird feeder with 0, 1, 2, and 3 quarts of seeds weighing 2.3? Trying to read my numbers. How come I got an extra comma in there? Oh, you have 2.3 pounds, 6 pounds, 9.7 pounds, and 13.7 pounds. I didn't put spaces in. I'm sorry. Respectively. You gotta add the respectively at the end. I don't know what that does, but it looks nice, doesn't it? So I'm going to pause it. Everybody make your table. Go. Okay, so I came up with a T-chart that dealt with Q and W. Q stands for the number of quarts and W for the weight in pounds. So 0 pounds, 2.3, 1, 6, 2, 9.7, and 3, 13.7. Is everybody okay with that?
Yep.
Write the data as ordered pairs. I'll give you guys a couple seconds on that one. Remember, we're just writing them. We did this yesterday, so it should actually be no big deal. So I took the liberty of doing that. From here, it's not asking us to graph it in part D, but part D says state whether the function should be discrete or continuous. Explain. Maybe, let's just graph this. Just kind of decide. Notice that there are no negative numbers. So I'm going to stay in the first quadrant. I'm going to put 1, 2, 3, and go by ones here, but I'm going to make the scale a little bit smaller. Is that okay? Kind of went through my points. Sorry. So 0, 2.3, give or take. I'm going to change colors so that we can see this a little bit better, I think. 0, 2.3 is there. 1 comma 6. There. 2, 9.7. Is there. And all the way up to 4, or not 4, is it 4? 3. 1, 2, 3. 13.7. It's there. It's not perfect, as in maybe it should be a straight line, but as the points should fall in a straight line. The question is, should I leave it like this? Or should I make it like this?
Like that.
Option 1 or 2? 1, or 1, 2. 1, or 2. Why 2? Fritz. Well, if I put the line on there, I know it's continuous. Why can we say it's continuous, Fritz?
Because the points are constant.
Well, it's just because they're in a straight line doesn't mean we have to say it's continuous. Because right now I got a continuous graph. Now I have a discrete graph. Now I have a continuous graph. Chuck. Basically, he's just telling us what? Ready? Well, when we connected it, we're forcing it to be a continuous graph. But I'm trying to figure out the situation in general. Would this be would we want to connect them or not? I agree, I think we should, but what's the reason why? I want to say it's continuous. Matt?
Because it was like half a point, it'd still be like more weight than that.
Yeah. Guys, just because he's telling us at certain times the weight will be at certain quarts, what if he only puts a quart and a cup in? Or 1.5 quarts, 1.75 quarts, 1.83 quarts. What if he overestimated or filled this little quart jar thing a little fuller? It wouldn't be really a quart, would it? But it would still weigh more than the last time. So it makes sense that there is something going on between the dots, isn't there? If the bird feeder could hold up to 3 quarts, actually, if that's the case, then maybe I shouldn't even have this over here, right? It should stop. But you can fill it with anything in the range from between 1 and 3 quarts. I could fill it with any of these. No, I'm racing now. Wrong one. I could fill it with any value of quarts down here, and it will give me a Y value or a weight value. That's why. Everyone was right. It's just that I wanted to flush out the exact reason there. Now, let's take a look at graphs. Let's decide if something's a function or not a function based off just looking at this. Now, wait a minute. We said a function was what again? It's a relationship, yes. But what was more than that? Exactly 1 output for every input. So therefore, we can do something we call the vertical line test. The vertical line test says, if any vertical line intersects a graph more than once, then it's not a function. On the flip side, if you draw a vertical line and it doesn't hit twice anywhere, then it is a function. Now, this is the thing that gets kind of complicated for students. It's easier, guys, to prove something wrong than it is to prove something right. I'll give you guys a challenge. I always use my left blinker when turning left. Is it going to be easier to follow me around for the rest of my life every time I drive my car? Or just happen to be driving behind me or seeing me on the road, turning left and not using it once? I was just saying, you catch me one time doing something I said that I'd never do, you prove me wrong, right? But to prove that I do it right, you would have to watch me every single time doing that. Is that even feasible? No. I don't think it's feasible. So to prove something wrong is easier than proving something right. Because all you have to do is give one counterexample and they're wrong. So, looking at this, I got three functions, or three graphs. Two are functions, one's not. Why is this so? Because if I draw a vertical line through here anywhere, how many times does it touch that graph?
One.
Just once at most. And then someone's going to go and say, okay, that's not a function. Or that's a function, sorry. But I could come over here. I'm going to change colors so we don't mix them up. What happens if I go here? Look at this graph. Hey, it didn't touch it at all. That's a function. Isn't that just one example that it does work? That doesn't work that way. And so I go here. Look at this. I could go right on the y-axis. How many times does it touch there?
Twice.
No, on the y-axis. Once. It still works. But as soon as I go over here, what happens? The graph is touched twice, therefore not a function. Now wait a minute. Let's think about what it meant when we said exactly one output for every input. Guys, guess what? I'm putting this value in right here, right, for x. That x value said that it's going to go up to here, or it's going to go down to here. That's two different options. That's not functioning correctly. That's like the same button going to two different things. That's a no-go. Guys, take a couple seconds. Tell me why or why not you believe that the third one is function. Maybe it's wrong. Maybe I'm trying to fool you. Start drawing some lines. Tell me, function, not a function. Give me an example of something that works or doesn't work. Preferably the one that doesn't work, because that would prove it's not a function. Does it work? Still works to me.
Oh.
Does it work? 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 They all work. Everybody's like, hey, wait, Mr. Conchak, follow the y-axis here, right? Does it work?
No.
This one's an interesting one.
Well, it's not really a relation, is it?
It's a relationship.
No,
All these are relationships, guys.
Yeah, that's right, but
Is this a function, though?
no, it's not.
Yeah.
It is because like the one on the top is like a simple input in, so it's like half that.
Right. Good observation, guys. This circle up here is open, while the one below is closed. What does it mean to have an open circle on a number line? Is the number included? No. So therefore, on the top line, or top part of this function, this dot's open. It's not included. But if you come down here, it is. So these two actually are not overlapping. So therefore, this is a function. So be very careful on that. You got to watch what's open, what's closed, what's included, what's not included. So now, in the last part, we're just going to give you equations. You have to determine function, yes or no. The whole idea here is make a t-chart. Find values that make it true. Okay, so what if I put in 1? If I put in 1, what's y have to be to make it true? Well, that'd be 3 times, negative 3 times 1, which is negative 3 plus what equals 8? 11. Is everybody okay with that? Do the same thing. Put in 2. Then you get negative 3 times 2, which is negative 6 plus something equals 8. 14. Let's try 0. What happens when I put 0 in for x? 0 times anything is. So it'd just be y equals, 8. Hey, that's not too bad. Ooh, what if I try negative 1? Negative 3 times negative 1?
So it's 5.
3 plus y equals 8. Well, then y has to equal 5. Is everybody okay with finding points?
Mm-hmm.
I just plugged in x values, substituted in, used the kind of technique that we did, I don't know if it was the last lesson, but the lesson before, where we had to solve equations by kind of knowing what it is, or kind of thinking about it. Okay? So, graph them. And 1, 2, 1, 2, 0, 8 would be easiest one. Two 14. I think I made that all the way up to here. 1 11. And negative 1 5. Your book wants you to connect all of these as well. Because if I kept on adding values in, obviously there's more than just the nice numbers that make it work, right? I could have chose 2.5 and found y then. So the question is, does this pass the vertical line test?
Yeah,
Yes. So therefore,
it's a function.
it's a function. Because we have to worry about more than what we have in our chart, because those are just a few of the solutions to that equation. There's an infinite amount that goes in both directions. Next one. Wait. If I put in, wait,
We need a y.
there is no y. We could solve this and say, wait a minute, we can't do this. We just have to say x equals 2? Ooh, does anybody know what kind of graph an x equal 2 is? Wait a minute, I crossed out the t-chart. I shouldn't have done that. Because x equals 2, so it means if x is 2, can y be?
Anything.
Anything. Ooh, it can be a 3. Oh, if I put 2 in again, what can it be? 4. I put 2 in, I'll be a negative 5. Can you graph those?
Yeah.
Okay. I'm going to get this out of here so that we can get some room. Two negative 5 is down here. 2 4 is here, and 2 3 is here. If I connected those, it forms what kind of line? Vertical line. Will vertical line pass the vertical line test?
No, so it's not a function.
So, no, I can't draw a vertical line there that doesn't touch another point. So therefore,
It's not a function.
not a function. Homework is chapter 1.7, page 52, 20 through 44, every 3. Have a great day.